This week in Chapter 13, we're going to be learning about fluids. One of the things we're going to learn is that pressure in a fluid increases the deeper that fluid is. So I know you've seen these water towers. They're very common in North Carolina. And the reason these are used is by piping the water up to a really high height. That means the depth of the water at ground level is pretty deep. It'll be the height of that tower. And that height is going to provide enough pressure to push that water to all the houses in the city where the water tower is used. This is a form of hydrostatics. Hydro meaning water, static meaning motionless. All of the calculations we're doing in this chapter is going to be hydrostatics, where the water itself is motionless. One of the other things we're learning in this chapter is about buoyancy. Now, this picture is kind of crazy. These students built their own concrete canoe, and we're going to learn how something as crazy heavy as a concrete canoe could still actually float. The buoyant force is responsible for floating, and another word for it is Archimedes' principle. We'll learn how to calculate those as well. Now this chapter is very small, especially compared to some of our earlier chapters this semester. So this is an extremely abbreviated version of what we're going to be learning in this chapter. We're going to learn about density. Now if you've had chemistry, you know what density is. It's mass divided by volume. Those units are going to be kilograms per meter cubed. We're also going to learn about pressure. Again, if you've had chemistry, you may have seen this before. Pressure is the amount of force spread over an area. So its units are newtons per meter squared. Another unit for that is pascals. But as you'll see, lots of people have different units for pressure. We'll learn how to calculate the pressure of a liquid at depth, because the deeper you go in a liquid, the more pressure there is. We'll be using this equation, that total pressure is equal to ambient pressure plus rho dg, and that rho naught is the atmospheric pressure. Most of the time it's air pressure, 101 pascals. We'll also be learning how to calculate the buoyant force, and I'll go through this in more detail. About half of these slides cover the buoyant force. So the first thing we're going to talk about is fluids and density. A fluid is something that flows. That's what fluid means. Liquids and gases both meet that definition, that when you put them in something, they will flow and move to fill, or they will change shape to become the same shape as the container. Now I've seen some videos or pictures saying that cats are fluid, because they show some crazy pictures of cats in sinks and all kinds of things. Cats are not fluid. Only gases and liquids are. There's a big difference between gases and liquids. Gases are disconnected atoms, as shown in this picture. They're just bouncing around all over inside their vessel. Now you can compress them closer very easily because they're not actually connected. A liquid, on the other hand, those atoms are very closely connected. And if you press on a liquid, it doesn't really change. It can change shape, but it's not going to change its volume. So the first place to start is to define a mass density. That's the mass of an object divided by the volume it takes up. And of course those units are going to be kilograms for the mass and meters cubed for the volume. We use these units. Chemists often use grams per centimeters, which is slightly different. But in this course we're using kilograms and meters. So for example, gasoline has a density of 680 kilograms per cubic meter. That means if you were to get a container that was exactly 1 cubic meter, poured it full of gasoline, the gasoline would weigh 680 kilograms. So this table you might want to keep handy while you're doing your homework. It shows the densities of a variety of substances, a variety of fluids. The gases are up here, and you can see gases, like I said, they're disconnected molecules, so there's a lot of nothing in between those atoms. So the density of gases tend to be very small. Then here are some densities of liquids, gasoline being the smallest, and mercury, which is that, right, you know what mercury is, that silvery, really heavy silvery liquid, is the most dense. Water here at 1,000 kilograms per meter cubed, and seawater, because of the salt, is slightly more dense. Again, you don't have to memorize these, but you may want to keep this table handy while you do your homework. Of course, you can Google these values as well. So here's just an example. We can calculate the weight of the air in your living room. If we say your living room is 4 meters long, 6 meters wide, 2.5 meters high, and we can use the density of air as 1.2 kilograms per cubic meter. So we're just going to use the equation for density. That density is equal to mass over volume. We are given the density, we are given the volume, or at least we're given enough that we can calculate it, and we're asked for the mass. So we can substitute in what we know. So we're going to assume that your living room is rectangular. So we're just going to multiply the length times the width times the height for a rectangle in order to calculate its volume, and that's going to give us that the mass in the air is 72 kilograms. Now that's about 150 pounds. Now, the first time I saw this calculation, I was really very surprised because we're just used to the air all around us, and it seems like nothing, but it's actually not nothing. It's quite heavy and substantial. Oh, and so one other thing before I get off this slide, a lot of the homework problems will have lengths in centimeters, so it's important to remember how do we convert centimeters cubed to meters cubed. How do you convert a unit when that unit has an exponent? Now if you remember, because of the exponent, you're going to have to use the same exponent in your conversion. So there's 1 cubic centimeter. I'm going to use my straight line method. So there's 100 centimeters per each meter, but because this is cubed, you need to do it 3 times. The other way to look at that is you could just put parentheses around this and cube your conversion. Either way, you need to know that 1 centimeter is 1/millionth of a cubic meter. So the key concepts for this section, yes, very short section. Density is represented by rho, and it's equal to the mass divided by volume. The units are kilograms per meters cubed. And remember, when you're converting between cubic centimeters and meters cubed, there are 1,000,000 cubic centimeters per meter cubed.